Alrighty, guys. So next speaker is Professor Melnikov. He will start his lecture with model-based cluster analysis. Please.
Thank you very much. So over these 7 lectures, I will be talking primarily about model-based clustering. This is going to be the major topic, basically. But we will take a look at model-based clustering from very different angles. And I do not assume that you all know what mixture modeling is or model-based clustering is, but as a matter of fact, I know that some of you are quite advanced in this area, particularly doing PhD dissertations. But also, a small survey. Can you please raise your hand if you heard about finite mixture models? Okay.
I learned it from the program, from the title.
Thanks. So I think the plan is the following. We will start with pretty much with basics. So even if you don't know what mixture modeling is or model-based clustering is, we will discuss everything you probably need to know in order to follow up with more advanced stuff. I will try to incorporate as many examples, real-life examples, some illustrative examples as possible. Okay. Now I need to figure out how do I switch to the next slide? Just
no.
Nope.
Up.
Up. Nope.
No.
Just a click. Double click. Nope.
Okay. Maybe you should escape the phone.
It should work.
Maybe. It was moving when you were not in the just exit the full scale and it was moving there. No, not anymore. Oh, well. No, I think it's not looking like that. What are these things? I'm afraid of touching it. Well.
Let me just go back to the. Yeah, I'm just going to try to reset the settings that we have changed here. When we have this input mode on the system. Input mass of 100.
Next page, right page.
Okay, we have this keyboard setting now.
Oh, there's a pen, maybe this guy will.
Yeah, just a second. Now try it.
But no, there's a pen.
Yeah, the pen is for this one.
Oh.
The pen is for this one, but should do the job. Yeah, okay, I'm gonna just exit the. Okay, excellent. You should do the job.
What is the software? Thank you. All right. So I will start with that very brief bio sketch so that you would know a little bit about me. So originally I'm from Ukraine, was born in Kharkiv. I finished, like, you see there are too many lines, so I dropped my undergraduate education, but I received it in Ukraine. It was from Kharkiv Polytechnic University. Then I went to Bowling Green and joined master's program in applied statistics, finished 2005. Then I did PhD in Iowa State, finished it in 2009. And then for 3 years I lived in North Dakota in Fargo, worked there as an assistant professor. Then I switched to Alabama, and this is where I stay now. My primary research area is cluster analysis, classification, multivariate statistics, and I am, like in the recent years, I was pretty much involved in this area. I was on the board of directors for the Classification Society of North America. By the way, if you never heard about the Classification Society, and if you are actually working on some problems related to classification, there is annual distinguished dissertation award, and students, there are, depends on the year, but usually there are many submissions, very good submissions from dissertations, and if students basically compete for some prize, and also they get invitation, basically completely funded invitation to come to wherever this conference is going to be next year. And you do not have to be from the United States, by the way, in order to apply for this award. And also, so in addition to publications in this area, I also produce like art packages. Not too many, but at least for those methods that we consider important, we try to create art packages. All right, so here is the outline of all the lectures. So first of all, we will talk about cluster analysis. We will talk about model-based clustering, how it's related to cluster analysis, and we will also talk about finite mixture modeling. Then we will talk about slightly more advanced stuff. I think this introductory period will, like, probably it will take around 3 lectures basically to go through the first 2 items. Then we will talk about modeling metrics and tensor unit data, semi-supervised model-based clustering, time-dependent categorical sequences, and there is also some very recent development in finite mixture modeling with stylometry that I would like to show you. All right, so cluster analysis. The objective of cluster analysis is to find groups of data, and we want to find such groups that observations within these groups are going to be somewhat similar, and groups themselves are going to be relatively distinct. Once I submitted the paper and the word relatively was not there, and the reviewer said you have to put the word relatively in there. So now I always put relatively distinct in every objective of cluster analysis. So, but this is actually, if you read like this definition, it sounds like a little bit vague, right? First of all, what makes observations similar? We have to have some rule that based on which we will decide whether observations are similar or not. Also, what is distinct groups? And this question is very closely related to the question how many clusters do we have here? And okay, this is not an arbitrary example, but I wanted to show you that probably detecting the number of clusters, even in the 2-dimensional situation, is actually the tricky part, right? Probably, like I assume, how many of you think that we have 2 clusters here? How many of you think that we have 3? Yeah, right. It really depends, I think, on how you define a cluster. So strictly speaking, there can be even one, I think. Like it all depends on how you define a cluster. And this example, very similar example, I read 2 books recently on model-based clustering, very recent books. In one example, this cross-looking cluster was presented as an example of one cluster, and in another book it was presented as an example of 2 clusters. Okay, so, but what I'm trying to say that there is this area is not as arbitrary as many people think. Like, and we will take a look at it. So many different clustering algorithms exist. Some most popular algorithms are hierarchical clustering, k-means like k-means, k-means, then spectral clustering, density-based like DB-scan, grid-based clustering, and model-based clustering. And I'm going to talk about model-based clustering. But before that, I wanted to also talk about some common beliefs about cluster analysis that are very popular, and even among people who work with the data. One common belief is that clustering is an arbitrary and highly subjective process. And even in my department, I can tell you, we have, like, I had conversations with some faculty members, and some faculty members do think that arbitrary is the right word for cluster analysis. Basically, if you don't like one method, just choose another one and you will find something better, and just fish for a good clustering solution. Okay? This is one common belief. Second common belief is that standardizing data before clustering is a good idea. So first we will talk about these 2 beliefs, and after that we will continue. Okay, so here is my example. There are 4 solutions obtained by different clustering algorithms. So here I just used k-means, and then hierarchical clustering with 3 different linkages, complete, words, and average. And as you can see, all clustering solutions are actually different. And so which one to choose? Like, according to the first belief, you choose the one that you like, right? Basically. But at the same time, I wanted to show you something related to k-means. So k-means, probably most of you at least heard something about k-means, right? It's a very popular clustering algorithm. So the idea is we typically choose k-seeds from the data. We assume that these seeds are going to represent cluster centers, and then we assign all other observations to the clusters with the closest cluster center. And then for the obtained partitioning, we recalculate cluster centers, cluster means, and we repeat this process until we get a stable solution. But this k-means probably is by far the most popular clustering algorithms. And I believe there are 2 reasons actually. Okay, maybe 3. So speed is one of them. We do not need to do any numerical computations. We do not need to do any matrix inversions. Everything is very simple. Easy construction, like basically these are the steps that involve k-means involves, right? Includes, and the third reason that I didn't mention here, I think that everybody can understand it. So sort of the attractiveness of k-means is that everybody understands k-means. I'm not saying that k-means is not necessarily good, but it's like we have to know some things about k-means. So if you take a look at my very first example here, the plot, you can see that I have points represented in 2 symbols, right? There are dots and there are crosses. So, and these are original, these symbols represent the original cluster. sign. Okay, so because I simulated the data, I actually used just two Gaussian distribution to simulate the data. But because we use k-means by construction using Euclidean distances, right? Look at what happens if we run k-means on this for this data. You can see that basically this blue cluster that is quite well distinct, right, separate from the red cluster, but these points, all these points are going to be closer, right, to the blue cluster, and because of that, yes, okay, so symbols represent the estimated assignment, okay? Okay, color represents the original assignment, and symbols represent the estimated assignment. So you can see that all these points got assigned to the same cluster with the blue one. Yes, makes sense? So, okay, so this is what happens in case of elongation, right? If we have an elongated cluster. What about spherical? Actually, okay, I consider here two spheres of different sizes. You can see that the points at the edge also fall, also incorrectly classified. And this is the ideal situation when k-means is going to work. This is the case when you have spherical clusters of roughly comparable sizes, and actually proportions of points have to be also the same. So basically, this is my point here that k-means, of course, it's a reasonable algorithm, it's a good algorithm, but we have to run it only if we expect that our clusters are spherical and have roughly the same size. And it's important in some applications, but as a general clustering tool, I wouldn't recommend using k-means if you don't know something specific about your data. So my message here is that the model you're using, right, the method you're using has some properties, right, and you have to take these properties into consideration when you're looking for the clustering solution. To some degree, it reminds me, like if you think about regression analysis, right? So clearly there is a quadratic pattern, right, observed here, and I just drew a linear function. But I'm not saying that, oh, regression is arbitrary, right? Just try one function, another function, and choose the function that you like in the end. So I think there is some similarity between these two examples. So basically, the cluster, the method you're using in the cluster analysis also defines the obtained solution, right? So we have to be careful. It's not that we can choose any method basically and end up with equivalently good results. Okay, about second belief. So many clustering algorithms such as k-means or oftentimes hierarchical clustering, they rely on Euclidean distances. And in order to get rid of some potential discrepancy in units, people often recommend doing standardization first. And the idea is the following. Of course, if you have some variable presented in meters, right, and another one maybe in miles, one variable can completely dominate over the other ones, right? But this idea, of course, is interesting and meaningful, but we have to be very careful about this as well because it's a dangerous idea. So we have to remember that when we standardize the data, there are actually two sources of variability in our data. We have within cluster variability and between cluster variability. And when you standardize everything all together, you ignore the fact that there are two sources of variability. As I illustrate in this picture, so you can see that this is like nearly perfect clustering solution obtained by k-means. And this is what happens with this solution if I basically do standardization, right? Because when we standardize, we're trying to get everything to hypersphere, right? And basically, because of that, the clustering solution is going to change. And standardization changes our data. So we have to be at least careful about standardizing the data, because we have to understand that it may change the solution and properties in our data considerably. Okay, so what should we use? I think actually we can use some methods that instead of Euclidean distances, use some other distances such as Mahalanobis distances that automatically standardize the data. As we will see a little later. Okay, so now let's talk about the introduction to finite mixture modeling. We are familiar with textbook examples like when we have data coming from normal distributions like chi-square, uniform, other distributions, but in theory is quite well developed for these distributions, but in reality most frequently looks like this, right? Or much worse than this. And in this case, we cannot immediately apply one of those famous distributions to model such data. So what can be done instead? We can, actually this is what I did here, you can hopefully see, there are green, red and blue lines. There are several distributions mixed, 3 normal distributions mixed in this example, okay? So this is an example of basically what is called the finite mixture model. And this is how it is formulated. So X is going to be capital X. It's a random vector. By default, unless I say otherwise, vector is going to be p period. So p will stand for the length of the vector. Capital K here represents how many components we have. Each distribution will be called a mixture component. Capital K, once again, is the number of components, pi k. There are several names for pi k. Most typical, and this is what how I'm going to call it, it's mixing proportion. Sometimes people call it prior probabilities, mixture weights, etc. But I will be calling the mixing proportion. Because we want to have a legitimate distribution, we have to put constraints on this mixing proportion, so they have to sum up to 1. Right? This is our constraint, and of course these are they have to be greater than 0. Theta k, this is the parameter of our component fk, and the functional form of fk is typically assumed known. In reality, of course, we do not know what's the best model we can get, but we will talk about this a little later. So I think I talked about everything, right? So okay, so fk, once again, this is component, pi k mixing proportion, kth mixing proportion, and capital K represents the number of components. And these parameters theta k is component specific parameter that we need to estimate usually. So, okay. Among mixtures, Gaussian mixture models are by far the most popular. And in this case, these fk just have the form of the Gaussian PDF, multivariate Gaussian PDF. And if you take a look at my last bullet that I say employs Mahalanobis distance in PDF kernel, this looks like a standardization pretty much, right? So this is why basically employing these methods within finite mixture models, like Gaussian model, can actually produce better results because it can standardize clusters sort of on itself, right? So it can effectively replace basically that standardization step. This is what I'm trying to say. All right. So there are many different procedures available for the estimation, but maximum likelihood estimation is by far the most popular. Do we know what the likelihood is? Okay, good. So, okay, and the typical algorithm for maximum likelihood estimation in finite mixture modeling framework is called the expectation maximization algorithm. The algorithm was proposed in 1977, and this is a strictly climbing procedure. So at every iteration, you get a likelihood value higher than the value at the previous iteration. So you cannot observe drops. And this is actually very convenient when you write your own programs, basically, because you can always take a look, and if your sequence is not increasing, then you're in trouble. Something for sure is wrong. Okay, so how does the EM algorithm work? The EM algorithm assumes that there is some missing information in the data. And in this particular case, it can be really missing information, or it can be information that we pretend to be missing. Okay? In this particular case, we can pretend that each data point came from one, like, do you remember my example with 3 Gaussians, right? So each data point, when I simulated, came from one of the Gaussian distributions, right? So basically, if I assume that Zi will stand for the label for my observation Xi, then I can get what is known as complete data. So complete data is a combination of my observations Xi and also Zi's. These are group labels for observation. And then I can construct what is called complete data likelihood function. So this is how it would look like, complete data likelihood function. Okay, first of all, probably I need to tell you why do we care about even complete data likelihood function. It's like, if you take a look at the previous page here, right? If I construct likelihood, and let's say in IID case, when everything is independent, right? I would have a product here, right? From I, from 1 to n, and then I take a log, and as a result, I will get sum of the log of the sum. And of course, it's not very nice form, right? We would prefer to have, actually, we would prefer to have a product, right? Because then when we apply log, right, everything will become a sum. So this is the only reason why we are concerned actually about this complete data, just to make the functional form more convenient for the optimization. All right. So, and then this is why we can write down the complete data likelihood function, and this is how it's called. But the EM algorithm does not work directly with the complete data likelihood function. Instead, it works with the conditional expectation of the complete data likelihood function given our data. So this function is historically denoted as the Q function, and basically, this is what happens here. I just take this complete data likelihood function, apply log, and take the expectation. You can see this expectation here because Zi is the only random variable here. All right. It is like it's just a sketch, but this is how you can get basically the formula for the probability. Tau ik. This is how I'm going to call this. Probability, this is a posterior probability that observation Xi originated from the K component. So it's basically, you see this expectation of the indicator function, it's a probability, conditional probability, and you can just apply this to get the formula for the posterior probability. Okay, so here also some new notation. 2 dots on top of the parameters and probabilities are going to represent the current iteration. Because you will see lots of EM algorithms in during these classes. And so one dot will represent previous iteration, two dots represents the current iteration. Okay, instead of putting number of iteration in parentheses because they compete with school years and etc. So that's what we're going to do. Okay, so this concludes the E step. E step, E stands for expectation. This basically conditional expectation of the complete data log likelihood function. This is what we need to achieve at the E step. And in our setting, like EM algorithm is applicable to many different problems. But in finite mixture modeling, typically the EM algorithm reduces just to the calculation of posterior probabilities as here. Okay? Unless there is something else missing, because there are many other problems where like some observations may be, for example, partially unavailable. All right. What about letter M? Like, because we have EM algorithm, M step stands for maximization. At the M step, we just need to maximize the Q function with respect to parameters. And tau ik, you can see it's already basically fixed. We have taken it from the E step. So we basically need to optimize the function with respect to zk and pi k. And EM algorithm is, as I said, is an iterative procedure, so we repeat E and M steps until we reach the convergence. And upon convergence, our maximizer zeta hat is going to be actually the MLE. So maximum likelihood estimate. So this is a very popular way how we can get MLE from like for finite mixture modeling in the finite mixture modeling setting. Some issues that are typically reported for the EM algorithm: slow convergence, initialization, stopping criterion, etc. Out of these three that I listed here, I think the really serious problem is only initialization. Slow convergence, I think people keep talking about slow convergence since, maybe, I don't know, when the computers were not available, okay? Because as you could see, EM algorithm was developed in 1977, but indeed at the same time, I want to say that there are problems where you actually fight for every improvement in terms of speed of the algorithm. And in particular, like many problems are actually very time consuming. And like when we write R packages, for example, we typically write like the draft version in R, and then we translate everything in C and basically just use an R function just to call C program. Okay, so because also reviewers always ask questions about what's the speed compared with other methods. When you write your programs in C, basically, typically this comparison will be favorable. Okay. All right. So okay, in Gaussian mixtures, I already said they are by far the most popular. If we consider Gaussian mixture, we can get the following solution. Basically, this is E step, M step. These are the formulas that we can just employ, and this is the stopping criterion that I typically use. This is a relative change in log likelihood values obtained from two consecutive iterations. This is probably very easy, but I do not recommend ever actually using, at least in this setting, stopping criterion based on parameters, because I remember my first program actually in the EM algorithm, I tried to base my convergence criterion on parameters, and actually I was waiting for convergence, and my model involved something like, I think, 700 parameters, different parameters. And I was waiting and was observed that basically when you reach the convergence in, like, let's say 698 parameters, then 2 parameters will be a little bit off, then you reach convergence, and then one runs away, etc. Okay, so basically, unless your model is very simple, it's not going to work. So the stopping criterion has to be based on the function, on log likelihood function. All right. Now we will talk about the information criterion that can be useful for model-based clustering. But before that, I wanted to say that when we looked at the picture, right, we could decide 2 clusters or 3 clusters because we can visually inspect the data, right? So in 2-dimensional situation, or maybe in 3-dimensional situation, things are relatively easy, right? Like, of course, like even then we didn't know how many clusters actually are there. But imagine a situation when you have like 10-dimensional data, for example, right? You can take a look at the projection, but very likely you will actually have lots of overlap, right? And when you reduce the data. So you never know actually how many clusters are there just by visual inspection. So it's a very challenging problem. And of course, visualization would be very helpful, but it's far from being trivial in this situation. So, also, excuse me, if we had the chance to visually inspect the data, we would be able to choose maybe a model appropriately, right? Not only how many clusters, but what kind of model. Like, is it elliptically shaped clusters? Do we have skewing? Do we have heavy tables? Things like that. And because these visual methods are generally unavailable, what people in mixture modeling typically do, they use some information criterion to pick the model that provides the best fit with as few parameters as possible. Basically, this is what this AIC, this is Attack information criterion, BIC, Bayesian, proposed by Schwartz. So the construction of all these methods is pretty much the same. So the first part measures the fit of the data, and this is the penalty that penalizes, pushes in the opposite direction our function, right? And this is a function of the number of parameters. As you can see in AIC, the penalty is 2n, here it's m log of n, and because of that, BIC is considerably more conservative, AIC is more liberal. So, in mixture modeling framework, people who are actively involved in mixture modeling never use AIC. Okay? So you will, it's extremely rare to see AIC in the mixture modeling literature, because BIC is doing so much better, basically. There was an interesting idea proposed in France, ICL. They proposed basically BIC penalized for uncertainty. So this like entropy related term that is exactly the same as BIC if the classification is very crisp. So if everything is very well separated. But if we have more uncertainty in our classification, right? In this case, this penalty can be substantial. And the authors claim that ICL targets not necessarily detecting the optimal number of components, but rather the optimal number of clusters. Yes.
In which way is the IC more conservative? Is it more parsimonious, fewer clusters?
So you will find fewer clusters. AIC typically, and I think even not you see, there is also some literature that shows that BIC is consistent in choosing the number of parameters given that the model specified correctly. Okay, and AIC is actually very much off usually. Okay, so what do people then do? Typically, we try different models, if like whatever is available, and we choose the model that is the best based on one of these criteria, like based on BIC, based on BIC, let's say. Well, I would say BIC is number one criterion. ICL is also popular, but not as popular as BIC. Okay, and in addition to choosing the model based on BIC, BIC can do another thing that is very important for us. It can actually help estimate the number of components. This is how people estimate the number of components. So basically, you literally try k equals 1, k equals 2, k equals 3, up to k max, pre-specified value, and then you choose the model that has the lowest BIC value. Makes sense? Okay, some examples of how it can grow. Like there is a famous data set, Faithful, Geyser, and this is what the value, BIC value that I obtained, assuming that that we have spherical covariance matrices with equal volumes. Okay, so by the way, the data set is two-dimensional, so there are eruptions times and waiting time between the eruptions. And but what can we see from here? It seems that spherical solution, right? Spherical covariance matrices do not necessarily capture the structure and the data very well, right? It seems like there are some black points here, right? So on the edges, right? So right now the BIC value is 2354. So if we allow clusters now to be elliptical, you can see that we have like a reduction in BIC. And here I assume a Gaussian mixture model, but I allow now covariance matrices to be elliptical and to have different volumes and different orientations. And here I use the model that we call transformation mixture model. This is the model that can accommodate skewness, and you can see we have additional drop, another 10 points, right? So this is roughly how the process of finding the models can look like. And finding the good model is very important because I think this is exactly what I want to test. So real data are complex, okay? And this is why I really like the idea of mixture modeling and model-based clustering. Because in the mixture modeling setting, we can think, okay, in statistics in general, what do we have? We have a population, right? And we obtain a sample. Then we do something with the sample to get an idea about the population, about the parameters of the population, right? Well, generally speaking. Now assume that our population is heterogeneous. So it consists not of one population, it has subpopulations, right? Then each subpopulation produces a sub-sample, right? And then you can think about a cluster as a sample from a subpopulation. Then it actually is very intuitive way to think about clusters. So a cluster is just a sample from a subpopulation in the multi-population grand population, right? Does this make sense? So this is why this way of doing cluster analysis is actually very intuitive. And but as I already said before, the choice of the components will completely define the cluster shape. It's very important what you choose and how you choose components, right? Because if you choose distribution that doesn't provide a good fit to your data, of course, accordingly, it will be your clustering solution is going to be affected, right? So basically, finding a good model is very important. But in this setting, let me see how much time we have. A little bit. Okay, in this setting, this idea about connection of mixture models and clusters and clustering, it's appealing only if we have one-to-one correspondence between mixture components and data groups. In other words, when we can associate each component with a particular data group, right? But it's not always the case. Sometimes it's actually, sometimes it's difficult. Like, think about the situation when you don't know and you have no idea actually what distribution can be used. And maybe you use two Gaussian components, but your data group is skewed. Using several Gaussian components, you can easily model skewed data, right? But in this case, probably you are modeling just one group with several components. So, but then interpretation of your results becomes very troublesome. Okay, it becomes problematic. So, in general, there are some remedies, and we will talk about these remedies also a little bit later, such as merging mixture components. Basically, the idea is that if you have several components to model one data group, these components have to be so close to each other, right? They have to overlap considerably. If you have a way somehow to measure the overlap between your components, then maybe you can actually merge them based on that overlap idea. But again, model-based clustering is just one step away from finite mixture modeling. So basically, this is my last bullet. You basically assign each observation to the cluster with the highest posterior probability that you calculate from the step. Okay, so this is what model-based clustering is, pretty much. There are some variants, sometimes we do fuzzy clustering, but this is the most popular approach for model-based clustering. Okay, and I will just probably go over this slide and we'll continue tomorrow. So there are some challenges in finite, oops, there is X missing. Okay, in finite mixture modeling. And we will talk at least briefly, I will outline what the more or less real challenges in mixture modeling are. And the first one is regularity conditions. Sometimes people are concerned about regularity conditions and the entire likelihood related inference, but there are some remedies that are popular. Then, as I mentioned, initialization is a big problem. Then, as we just discussed, there can be possibility that one-to-one correspondence is broken, and then we have to do something about it. Variable selection. Actually, I'm not going to talk about variable selection much, but I will show you what's behind variable selection for clustering. The idea is like too much information, it might be actually very damaging. So we want to exclude those variables that do not contribute anything to learning about the clustering structure. Noise outliers, influential observations. Of course, as always, right, in the many model, they can be very influential. Stopping criterion, I will probably just skip. All right, that's the plan basically for tomorrow, and we'll do much more.
Okay. So as you as you said, that if we cannot visualize the data, then it's useless to use any partitional clustering algorithm. So we cannot know the number of clusters, any k-means or k-nodes, any kind of clustering. So I'm wondering about your opinion. In that case, if we apply the agglomerative hierarchical clustering algorithm, so there is a method that to find out the optimal number of clusters based on dendrogram by cutting the dendrogram from the point that achieves maximum difference between two consecutive cluster heights. So have you ever used this technique?
There are several actually. There are several methods how you can sort of make an idea about how many clusters are there. But I was just saying that sort of visualization would be very helpful, like as in 2D or 3D, right?
Yeah, so in many data sets it's not possible.
Of course, yes, yes. So,
What do you think about using k-means? Is it possible?
so for k-means, actually k-means, it's interesting. K-means can be basically, if you want, you can use something like BIC-like approach. Because k-means is a classification, like you can, it's equivalent to basically Gaussian mixture model with spherical covariance matrices, equal spherical covariance matrices, equal mixing proportions. And if you introduce just classification step, like there is an algorithm classification EM, right? So basically they're equivalent. So you can also measure the fit, at least to some degree. You can measure the fit and how much. Like you can use some criteria for that. Some people I think use it, but there are many other methods, right?
Yes.
So Kepler statistics, etc. Right.
Oh yeah, thank you. One is about the BIC. So there is some of the discussion about mixture model being singular. Maybe that probably like an alternative BIC for that.
So strictly speaking, BIC. That's actually a good question. Like, so BIC, strictly speaking, is not even completely correct in the setting for finite mixture model. But the thing is, it produces like really good results. It's surprisingly good, and specifically in this mixture modeling framework. Yes, I've heard a question very similar to yours. Like somebody asked Paul McNicholas, it's a like famous guy in mixture modeling from Canada, and pretty much he said the same. It's like, yeah, we know that BIC is not very good, like theoretically for this setting, but it really produces great results. So, but there are if I may continue, there are some alternatives actually. There is a popular alternative is testing, right? We can test instead of using criteria. What's the problem with testing? First of all, like all these finding distributions, it's almost impossible, so you need to use something like bootstrap. So you have to resample. Another thing is you need to decide on how many components you want to choose, right? So if you choose between 1 and 2, this is easy, right? You run, let's say, you feed the model with one component, you simulate your samples from this one component, you feed 2 component mixtures, 1 component mixtures, take a look at something like likelihood ratio test statistic, and you take a look, right, whether your observation, what you observe for your data is different or not, like how much different it is. But let's imagine that you reject. Okay, then you proceed to 2. You will test 2 versus 3, right? Okay, you fail to reject. Should you stop and conclude that you have 2 clusters, or should you continue to test 2 versus 4, because 2 versus 4 can be again significant. So there is also literature in this direction, and so like it's really tricky. And BIC produces sort of very nice practical results.
Okay, well, thank you very much. We next up, we'll resume in 10 minutes.